connected to the Chinese restaurant process. So just before lunch, a little bit about that. This is joint work together with Xavier Pennek from INRIA and Susan Hobbs from Stanford University. And the clinical motivation behind our work is, you can see here a set of CT images of the spine. On the left-hand side, you see patients that suffer from back pain. On the right-hand side, you see a group of patients that suffer from abdominal pain. And our goal is to find out if there are geometrical differences between the two groups. So these differences, as mentioned already before in the first talk and the discussion, what is the right basis to compare anatomies? Is there a basis that is as compact as possible and describes most of the transformations between the template and the patients very efficiently? And we are actually looking in this work to find this one type of way to find a basis. And this basis is described in terms of parts. So we have an image and we try to partition an image into different parts. And here you see a picture describing the idea. So we have a set of images. And from these images we are trying to estimate partitions. As you would see here on the right hand side, there's one example of a spine with different labels assigning names to different parts of the spine. And this is taken from anatomy books. And we're trying to do the same, but from data, learning from data, not from predefined medical knowledge. And here's an example on the idea behind our approach, something that was published last year at MIPS. You see here a reference surface model of a female body. And the authors of that paper acquired 56 different poses of the same person. And the task was to segment this surface into different subparts, so that are consistently moving according to some rigid motion. So you would say that your body is composed of different rigid bodies, like the arms and legs, and they move according to a certain motion. And they wanted to infer that from these different surface models without human intervention. And that's an example of their results, where the colors indicate different parts. And we want to do the same thing, not on surfaces, but in medical images, in this case for the spine. And you see here, the idea is to, we have a template that is somewhat centered at the population that we are trying to analyze. And from that template, we are looking for deformations that deforms the template into different patients. And you see here on the right, I generated some random deformations from the template. And what we want to do is to look at these deformations and identify different parts that move according to the same laws of motion in terms of affine motion in this case. And the starting point of our analysis are deformation fields that we compute with an algorithm, the Log-Demons algorithm. And there's different other algorithms that can do that. And the main idea is in these algorithms that the deformations are parameterized through stationary velocity fields. So the stationary velocity fields are our input, and we want to infer parts from the velocity fields for a given group of people. And we model this in a Bayesian framework. So we observe these velocity fields that describe deformations, and we describe them as different parts of the image domain moves according to some affine motion, which is parameterized with this vectorized matrix M, and multivariate noise at every vector position. So this is our Bayesian model, and the idea is to estimate the posterior joint probability of the coordinates and the deformation parameters. And in this particular case, we are more interested in the partitions, so we integrate out the deformation parameters. And we're looking for the posterior distribution of partitionings of an image, and incorporating all this uncertainty in that process and reflecting that in the posterior distribution. So there are two questions. One is, what kind of prior distributions are we looking for in the deformation parameters? And then how do we, what's the distribution on partitions? So I would like to address these two questions in the next slides, and starting with maybe a simpler one, how to put a prior on the deformation parameters. In this case, since we model the deformation with stationary velocity fields, there's a relation between affine transformations and stationary velocity fields that is given through the ordinary differential equation that we see here. And we can compute diffeomorphic deformation from an arbitrary matrix M through the matrix exponential here that you see here. And this gives us final deformations between a template and a patient. And what we're doing, so we're modeling this arbitrary matrix system, which are essentially the Lie algebraic representation of the affine group of transformations. And since they're arbitrary matrices, we can decompose them into different parts. One that represents rotation, and the other that represents scaling and shear, and the translation part. So we can regulate in our prior if we're looking for only rotations, or scaling effects, or translations, or everything together. And we chose a multivariate normal distribution on this, where the hyperparameters are, we can set and define which part of the affine transformation we are looking for and we are interested in. To relate this to something that might be intuitive for medical doctors, since we, in the end, we would like to get their information and use that as our prior in the estimation process. I tried to simulate what does it mean to draw multivariate normal distributions for the matrix M, and with a certain set of hyperparameters. And you see here the result of 100,000 simulations. On the left side, you see the rotation angle of the affine transformation, computed using SVD and Ricketts formula. And you see with a given set of settings of the hyperparameters, you see here that the angle of rotation it has its mode around 6 to 7 degrees. And then another interesting statistics might be the volume change for each transformation, which is around 1, so no change in volume from the template to the patient. And between divide essentially half the size of the template, or double, or 50% bigger for a specific region of the image. And so this allows us kind of a connection from the statistical formulation to the medical doctors that can say, so we're looking for this kind of scalings in our population, or this kind of rotation effects in my population, and connects the doctors, so include actually the doctor's opinion into the estimation at this point. And now maybe the bit more complicated version, and here is the Chinese restaurant process. It's a way to generate partitions of random variables, and I'd like to show a little example here to illustrate the idea. And if you start here with six voxels of an image, and we sample a link between one voxel and another voxel. We do this for all voxels. And the partitions are defined deterministically through the link. So if there's a link between two voxels, it means that they belong to the same partition. If there's no link, they don't belong to the same partition. So we write this down in a probability distribution that is proportional to a distance between voxels. And the distance, in our case right now, we choose to be 1 if it's a direct neighbor, and 0 if it's not a direct neighbor. And we have a parameter alpha that allows you to create self-links. So we create new partitions. And essentially that's the non-primitive part here, so the model adjusts itself to the complexity of the data. So it can generate more or less partitions as according to the data. And in a Gibbs sampler, this would look like this. We go through the voxels once we have a starting point, remove a link, sample a new link according to the probabilities that we saw before. And then there's essentially a few scenarios that can happen. One is that we form a new partition, so we split an existing partition into 2, Or if we just link back to the same voxel as before, we essentially keep the same partitioning structure. Another scenario is we delete the second voxel, delete another link. We link the current voxel to an existing partition, which essentially merges the two partitions together. If we sample a self-link, we get the same partition structure as before. So what I want to show with this is that you essentially have two different scenarios that can happen. One is you divide, you split one partition into two, or you merge them together, so you merge two into one. So these are the two things that can happen at one step of subset of the Gibbs number. At this point, these are just partitions that are given without any link to the data, so these are just random partitions of an image domain. And the link to the data is through model selection, in the sense that we're computing the marginal likelihood. So we're computing, given a raster field, how good is the model, the configuration of the partitions, how well does it fit the data over the range of all possible parameters. So here we fix a parameter of the noise, which regulates how many partitions we're looking for. We have the prior of the deformation parameters that we saw before, and we can essentially test for different configurations how well the model fits, and we can compare the ratio between different models. This comes here, so we go back to the partitioning, where we have either a separation or a merging of partitions, and we extend the probability distribution compared partitions that we saw before to include a Bayes factor that tells us if it's favorable to merge existing partitions or not to merge. And we sample according to this factor, and if it's more likely, if the data tells us that we should merge, then we merge according to that probability. If not, we split the partitions. So that's essentially the idea behind sampling partitions, giving the velocity fields with the prior deformations. And now I would like to show you an example to illustrate this idea. And here you see on the top, you have one velocity field with two rotations in different directions. On the second row, you see on the left arrows that represent links between voxel positions. And the color, if it's the same color, they belong to the same partition. And on the right, you see a maximum posteriori of the deformation. So the links on the left and the links on the right are not the same links. The right are deformations, and the left are the links between voxels. And what you see here is the Gibbs sample going through voxel by voxel, and sampling new links according to the velocity field that it's observing. And after a couple of steps of the Gibbs sample, so we count Gibbs sample steps as going through all voxels, that's one step. And you see here after a few steps, 1 or 2 steps, you get the results that we expected in this synthetic sample. Here I'd like to show a bit more complicated version of the same thing in 3 dimensions. So you see I generated a velocity vector field with 4 different parts. The scaling, the rotation, the translation, and the rotation. And you see here the view from different perspectives. And we run the same estimation, and we estimate, so I start with an image, a partitioning image, that essentially assigns 1 partition per voxel. It's a lot of partitions, and then the Gibbs sample goes through and samples again the partitions from the posterior. And you see here already at step number 2, we have a nice estimation of the different parts. And if you keep going, of course, there will be some, since it's probabilistic, there will be some fluctuations, but essentially it stays more or less stable like that. And then we have, so the color code is a bit different here, because in this case I tried to change the prior and to only look for rotations and translations and ignore scalings entirely. And you see here that it doesn't recognize the scaling part, the top part, but you can distinguish between the other three, which are the rotations and the translations. The same for scaling and translation, so I changed the prior, the deformation parameters, and we see that it picks up on the rotations and ignores the scaling and translation. Now, of course, so at the end, I would like to apply it for the real-world images for spines. You see here the template in the middle, as the spine template, and then different patients. So I use the log dimension register to obtain velocity vector fields between the template and the patients. And then from this set of velocity vector fields, we'd like to now estimate anatomically meaningful partitions. So I did this for 20 images, each for the abdominal pain group and for the back pain group. And these are the Gibbs sampler, posterior samples of the partitions at step 10 and step 20 and step 30. You see here there are some similarities, and you can regulate the number of partitions that you find through the noise parameter. And essentially, you see here that the back pain group has there's splitting into multiple regions in the middle part for the vertebra, and the splitting from the sacrum and the lumbar spine 5 into 2 parts. But our guess is at this point, you're only using 20 images out of 200 that we have. And the idea is to obtain a consistent, robust partitioning for both groups that should be hopefully the same, so that you can compare the two groups on the same basis. And our hope is that if when we include more images, that we emerge and we're going closer and closer to similar partitions. If that's not the case, then we probably have to analyze why are there different partitions for different groups. So then it would be a different problem, but not less interesting. So to conclude, we introduced a non-parametric way to partition images from velocity fields, where the number of partitions is not a fixed parameter. We learned that from the data, and the structure of the partitions is not fixed either, so it's the only constraint is defined through the distance function between voxels, which in this case allows to find partitions that are contiguous, that are not, it's distributed all over the image. We incorporate uncertainty in a Bayesian framework through the prior distribution of deformations and the partitioning itself. And we have this link that allows quite intuitive connections to medical doctors, where we can incorporate the prior from the experts there. And as next steps and open questions, of course now it would be interesting to analyze what are the actual deformations that we compute for each part itself. And if these and then compare these deformations between different groups and see if they yield different rotation angles between groups or different scalings between groups, and to summarize that and to compare, and use this for diagnostic purposes, of course, in the end. And as you saw before, the partitioning for two groups gives slightly different results. And the question here is really to see, as we include more and more data, if we can actually somehow converge to samples from the same distributions for partitions for two groups. So that's the idea. If that's not the case, we will have to look at how to compare these posterior distributions from two different groups.